Great, thanks, Lars. Of course, the detection of dark matter is, so far, hitherto, is entirely astrophysical. But those of us who do particle physics are always hoping that we can touch the dark matter on Earth. And that's what this story is about and has been about for a number of years. And I hope someday I'll be standing here, or someone will be standing here reporting that we've finally touched the dark matter. OK. So this is the LUX experiment, stands for Large Underground Xenon. And the contingent from UCSB includes myself, postdoc Carmen Carmona, Scott, Susanna, Kurt, and Dean. And you're here. And stand up. I'm going to make you stand up, OK? All right. So there's Kurt and Scott and Dean. And did we get Susanna? Darn. Wait, is she? I don't. Do I see her there? No. OK. All right. OK. So we have a really good team. Mike Witherell's up in South Dakota. So is Carmen. I saw them on the broadcast, actually, this morning. So part of why this was a big deal in South Dakota is this is kind of the scientific christening of the new Sanford Laboratory, named after Denny Sanford, who donated a lot of resources to this place. It's in Leeds, South Dakota, far western South Dakota, in the Black Hills near Mount Rushmore, and all sorts of other interesting things like Deadwood. It is the old Homestake mine. That's the Hearst family's mine that built the Hearst Castle up the coast and donated a lot to the University of California in the early days. It's now called the Sanford Underground Research Facility, and our facilities there are a mile underground. And it's had a long, complicated history over the last 15 years to get to this point of having scientific results. But no need for that. It's all just good news now, today. Here, there's a beautiful bike path beneath the headframe. The headframe is where the shaft that goes down about a mile where you start from. And here we are waiting to go down the shaft one morning. That is Carmen Carmona, and we wear all sorts of protective equipment. We're almost like miners when we go down. This is a drift. A drift is a tunnel that goes between the various shafts, and that's what it's like when we're walking to the experiment. Here's what it's like working in the experiment. Those are obviously hardworking graduate students, and me being the PI down there, I just take pictures and watch them. That's all. Here's Kurt Nurkorn, and this is the sort of fun thing that we get to do. We have a giant balloon in case we have to capture all the xenon. The 350 kilograms of xenon we have is quite expensive, and we cannot vent it. So if something goes wrong, we have a giant balloon at the ready, and we are practicing inflating it. That's the kind of good fun that we have there. There's me. I get to be a utility guy sometimes and remove manhole covers from the water tank. There's the LUX Collaboration, about 100 people, about 15 institutions, I think, and standing in the snow in front of the headframe. And you can see somebody photoshopped LUX there. It still says Homestake. They'd rather be in Isla Vista, where they were in 2012. And again, there's Mike Witherell, Carmen Carmona. I'm there. I saw Dean White somewhere here, and Susanna. They're in this picture, but I didn't find Kurt. I don't know if you got in this one. Yeah, OK. So they loved Isla Vista. The big picture is, as you know, in the last 20 years or so, a wonderful set of measurements have nailed down what is the nature of the energy in our universe. The dominant one is somehow stitched in with space-time itself and doesn't move around. Matter moves around, and there's two types, us, which we're a tiny minority of 5%, and the dark matter is something like 5.5 times as abundant as us. And that's the question, what is it? We know it interacts. All the information we know about it comes from wonderful astrophysical measurements, but can we touch it? Can we identify what particle it is? The avenue we're exploring in this experiment is driven by something called the WIMP miracle. WIMP stands for weakly interacting massive particles. And the concept is in the early universe, these dark matter particles here labeled Chi0 were in thermal equilibrium through annihilation with our kind of matter. And our kind of matter had enough energy to turn into the dark matter. And a very nice idea in the early universe. But then eventually, as things expand and cool down, these massive particles can still find each other occasionally and annihilate. And the remnant that survives will then be proportional to 1 over the annihilation cross-section. But the inverse process doesn't have enough oomph to go. So this determines what you have left. And the miracle is that a weak interaction cross-section and a weak annihilation cross-section gives about that quarter of the universe's energy. And that's it. For experimentalists, that's about all we need. Go do an experiment. Okay, yeah, about the weak interaction cross-section. And we take this as kind of a blurry weak. But of course, one of the remarkable things about this idea is that it's had a lot more legs, that you can engineer it into supersymmetry and describe the early universe, and there's a natural particle, and it just works surprisingly well, and maybe is right. So supersymmetry really likes this idea. Experimentalists just say, hey, we can cross that diagram and describe a dark matter particle scattering off our kind of matter. And so the concept is the dark matter will push on our nuclei and make them recoil. And that's what we're looking for. What are some interesting diagrams? I think the earliest idea is once you say weak interaction and dark matter particle, in the 80s, people said, well, the new particle is a Z0, maybe that interacts. And there's some interesting stuff here. The first idea was maybe it's a massive neutrino-like particle, and the Z0 carries a vector and an axial vector sort of interaction. The vector interaction was kind of ruled out very quickly. And the remnant one that that we're sensitive to now is the axial vector interaction with the spin. And that's something that LUX can address, but it's usually the second paper we write, not the first paper. The first paper came because here's the second boson that now has been discovered and is known as the Higgs boson. And so maybe the dark matter couples to the Higgs boson. How does you couple from a Higgs to quarks and nuclei? It's surprisingly complicated through quark loops and gluons. The nice thing is when you couple to the glue, it's a very simple interaction. It's a scalar interaction. Doesn't matter whether you're interacting with neutrons or protons. So it's isospin independent, and it's a scalar interaction. So that's the one we've been after for quite some time. Now, in something like supersymmetry, there can be loops of superpartners that also interact through gluons, and they can make the picture very complicated. They can maybe destructively interfere, or the mass of the quark gets involved. All sorts of things happen. You get a very low cross-section at the low end of weak interaction cross-sections through complex interactions of all these things. Or if you're at the high end, it's sort of 10 to the minus 38 centimeters squared. And there's always a little work to calculate the interaction cross-section with nucleons rather than partons, rather than quarks or gluons. But that's the range of the weak interaction cross-section we're looking for. The experiment we do is billiard ball scattering. And instead of, unfortunately, we don't have a table, we just have the Milky Way. And so here's the depiction of the nucleus of the Milky Way and the disk, and our sun is going around like on an old LP, but I don't know how many of you know anymore what an LP is. Okay, and this is the dark cloud that is really the Milky Way. Most of the mass in the Milky Way is in this dark cloud, sometimes called a halo, a dark halo. And there's the sun moving around, and the characteristic speed about 1,000th the speed of light, or 200 kilometers per second. And it's us moving through the apparent wind, if you like, of WIMPs, that is, the particles or WIMPs that we presume to be in the dark halo. As far as experimentalists are concerned, we can just think of them as at rest. Now, they're, of course, not at rest. Astrophysicists would kill me, or Scott Tremaine would kill me, I'm sure. Okay, but I'm an experimentalist. I'm allowed to be simple. Okay, and approximately they're at rest, but now, in the frame of the Earth, they look like they're coming toward you. Okay, and what's their density? Well, the density of mass around us is about half our kind of matter, averaged over a huge amount of astrophysical space around it, and about half the dark matter. And the dark matter is about is a mass density that's about a third of a proton, a third of a GeV per centimeter cubed. Well, actually, they are moving a little bit, and this is the sort of thing that we have to take into account. But with the typical experimentalist boneheadedness, if they're moving, which they are, it just gives us more energy to detect them with. So it's great. So fine. Okay. Now, there's a lot of discussion over what is the distribution and phase space of those things. We've all tended to agree on something really simple, just a Gaussian. And we know it's wrong, but we do it so we can all compare the experiments. Okay, so our experiment is billiard ball scattering with a dark matter particle as the cue ball. The mass we always used to favor was about the weak scale, because weak interaction, why not be the weak scale? And lately, all sorts of tolerance has been allowed and just encouraged to think maybe, plus or minus a couple orders of magnitude around that. Okay, but what's great about that mass is that if you stick a heavy atom like a xenon atom, look, its mass is about the same. So it's kinematically matched. Makes for sort of a nice experiment. If this gets much lighter than the target, then it can bounce off and not impart much energy. And that limits us when the WIMPs get really light. If this gets heavy, that's really no problem. Okay, that's not a problem. The kinematics, it just won't slow down. It'll still give a really nice impulse to that guy. Okay, we use xenon. I'll say why in a little while. And others have used all sorts of other targets. The most similar to xenon is iodine, and that's a little interesting because someone out there, the DAMA collaboration, thought they saw a signal with iodine. So xenon is sort of the closest on the periodic table. It's right next to iodine. So it's a little harder for them to escape a xenon result. Although, okay. And then if you just have to say, let's play some pool. You get about 1,000th of the speed of light imparted to the xenon for a good head-on collision. And of course, there's a spectrum of collisions, but that's sort of the kinematic limit. And you can calculate the energy in the recoil, 30 keV. Your dentist could detect that. So that's easy. Okay. The issue is not detecting this energy. The issue is two things. There's background. There are gamma rays all around us. And distinguishing a signal from that background is the issue. That's why we build experiments deep underground and shield them and so forth. And the issue is also knowing that it's a nuclear recoil and not the electron recoil that would come from Compton scattering. Well, by the way, so here's the first here's a more detailed look at what the number in some units, the number of events as a function of the recoil energy would be. And the shapes of these curves are dominated by two things, the presumed velocity profile of the galaxy and then some interesting form factor things from nuclear physics. But okay, one thing to look at is at very small recoil energies, there's coherence. Literally, there's coherent wave-like scattering of the nucleus off the WIMP or the WIMP off the nucleus, however you want to say it. And look at this. In a sense, xenon wins. It's got the biggest number of nucleons all packed together. You get coherent scattering off all 130 of them. And you win as the square of that. There's another phase space factor. Since it's velocity the galaxy delivers us, and phase space goes as momentum, the more massive the thing is, the more phase space you get, so the rate goes up. So you get this big bonus from using xenon. And that's one of the reasons we use it. Now, the coherence issue does mean there's sort of an uncertainty principle. It falls the fastest also. Okay, and that's what's going on. Okay, but we like xenon, but other people use other things. By the way, this is a log plot. The experiment is over these days by about that recoil energy. All this other stuff, unless we start getting high statistics WIMP interactions, we're not going to see the rest of this. To see the first 10 events, it's all this part of the spectrum. So you'd only have to look down there. Okay, so that's up to about 20 or 30 keV. Okay, let me shift a little and just start going into describing the situation. And this gives you the situation over time. So here, these searches started in the 80s, and assuming science is still funded in the world, will continue for quite some time. And what this is the cross-section per nucleon that has been achieved in sensitivity. Some people have positive signals, so let me just set that aside. The early experiments of the 80s, for example, that Mike Witherell and Dave Caldwell did that one. Frank and Avignoni and some other people did that one. Okay, this was actually at Homestake. That was at Oroville. Well, why were they doing that? They were doing that because this first thing we said, the vector interaction of the Z0 predicted a cross-section above 10 to the minus 39. And so they ruled that out. And then there was sort of an interregnum, and gradually people like Kim Greist at San Diego figured out that Higgs diagram really mattered. Okay, and experiments got going again. Okay, and then and supersymmetry, of course, is a way of life and has influenced everything. This Higgs-like diagram is sort of natural size. If you have a standard model size coupling there, it gets you to about 10 to the minus 43 centimeters squared. This experiment here was the CDMAS experiment that I participated in, and we got to our sensitivity sometime around 2005. Maybe we got a little more sensitivity later, okay? But that was the sort of target of that experiment. But basically, what's then happened, so you can sort of see the improvement as a function of time. There's sort of a change here. And what happened is these noble liquid detectors came in and have changed the slope of this line, okay? And our sensitivity that we'll put on today is going to be down in this region, okay? So the type of detector that you can see the nature of the different types of detector. Cryogenic, which are things like germanium, or there's some other stuff, supercooled crystals, sodium iodide. Liquid argon hasn't quite delivered. Is there a liquid argon point here? I don't see one. Liquid xenon. And then threshold detectors are literally bubble chambers, okay? Little bubble chambers where they're great, but they're a whole different discussion. Okay. So one thing that I'd point out is in particle physics, there are very few sensitivities that are gaining this number of orders of magnitude over this many years. There's an extraordinary improvement in ability to sense this, to search for WIMPs. Okay, so this is the sort of state of play with one or two modifications as of about a year ago. Okay, and so again, here's the WIMP nucleon cross-section. Here's the WIMP mass. You get the best sensitivity at masses similar to the mass of the target, masses of atoms. Okay, you lose sensitivity as the WIMP becomes light and barely budges the target. You lose sensitivity on this side because you need fewer and fewer WIMPs to explain the mass density of the dark matter in the galaxy. That's what's going on. What you see here is the limit curve from Xenon 100 in blue. They're the reigning world record holders for sensitivity. What you see is their experiment. These days, it's common to report an expected 68% range of sensitivity they expected from their experiment. Of course, any individual experiment can have a fluctuation. And then the 2 sigma also. And so anything below their curve is allowed. Anything above their curve is forbidden. And you see a bunch of my old experiments, CDMAS. You see a bunch of other experiments. You see some regions that are closed, which are people who more or less report positive detections. And they're all way above these lines. There's kind of 2 fronts in this battle, or in this endeavor. The race to the bottom, okay? And the race to the bottom also implies we're trying to build the biggest, cheapest detectors we can. That's important too, okay? There's also what I said, I don't know, I called it the left wing, okay? Moving that way, of trying to get to lighter and lighter mass WIMPs. You can see a lot of the positive detections cluster in the left wing, where there's the most background lives, okay? And the left wing has had a bunch of activity. The CDMAS experiment had 3 events, and that was their most favored point. The CoGen experiment up in Sudan, both of these are in Sudan where I used to work, has a region they like to say is very interesting. There's other regions in the regime, and you just sort of look at this and think, well, maybe something's going on there, right? Okay. And so something we did in the LUX experiment was we did everything we could to get our best sensitivity to low mass WIMPs. That means xenons that barely recoil, just to get nudged a little bit, okay? Let's see. And then there is something about the left wing that's very important. It's complementarity with the LHC. And I don't know quite why my animation went away. So it's okay. We don't need an animation here. Okay. So what's on this plot is a bunch of those curves that you saw. Again, it's mass versus cross-section. A bunch of those curves that we showed before. But there's some other things now. At the LHC, you can look for annihilation. You can run this diagram not as a scattering diagram, but imagine as quark-antiquark annihilation through a Z0 into non-interacting particles. And so how do you tell if there's nothing coming out of your detector? Well, you tag it with an initial state radiation. This is an old trick that also a bunch of my colleagues in graduate school did. And gluon is the best. And so it's a single jet or monojet in your experiment. And then if the interaction is really with the quarks, okay, to translate their limits on monojets to the dark matter plot, you need to make an assumption as the effective operator. If it's quarks, if this is a vector interaction, you can see you're about a couple times 10 to the minus 40. And what's beautiful about this is no matter how light the missing particle is, you get sensitivity. After all, they see missing energy from neutrinos that are massless. So you get sensitivity all the way to the lowest masses. There's no reason this could just go on to however far you want to go. The big issue is translating onto the plot of direct dark matter experiments. Okay, so if it's a vector interaction with the quarks, you see that. If it is an interaction through the gluons, of course, what the LHC is mostly is a gluon collider. And there's enormous density of gluons there. And if you have an interaction like this, look at the sensitivity you get. Okay, couple 10 to the minus 45, and coming up. In fact, the only experiment that really is getting better sensitivity under this interpretation is Xenon 100. Okay, so this has been a very painful, anxiety-creating problem in the WIMP dark matter community. And of course, whenever you're in that situation, you think you have a signal, you say, well, add another new particle to explain it. So to get consistency with these and the LHC, there's been the conjecture that maybe there's a second new particle. That is, maybe the interaction involves not this diagram, but a new diagram with a new intermediate boson that would be very light, maybe 10 JeV or 5 JeV or 1 JeV. So, some people would say they're adding a tooth fairy. Other people would say, no, they're just trying to fit all the data, and that's just a reasonable thing to do. But there's a whole set of experiments now at beam dumps looking for light new bosons. And that would be, if these things were right, if we really had dark matter that was light, maybe that's why it would be missed at the LHC. Okay, I've noticed in the past 5 years an enormous loosening of flourishing of ideas about like new bosons, all sorts of ideas what the dark matter could be. That has been going on in the last 5 years. Okay, and that's good generally. Let me tell you why Xenon is great. Large atomic weight, huge coherent factor. Okay, here's a shocker. It's very heavy. It has no long-lived radioactive isotopes. Argon has long-lived. The lighter noble gas has long-lived radioactive isotopes. Argon-39 is in the atmosphere. Krypton has a bunch of long-lived radioactive isotopes. In fact, one of our problems is krypton gets into our xenon, and we have to figure out how to get the krypton out of the xenon, which is hard. Okay. But that's great because that would give us background. If you have liquid xenon, it scintillates, or gaseous xenon, it scintillates all by itself with no additives. Most scintillator you need to add a magic molecule to. Okay. And the response is different for electron versus nuclear recoils. It's amazing. Okay. The UV of xenon is much easier than the other noble gases. We can use glass to get the UV out. We don't need either wave shifters or special crystals. Boiling point's above liquid nitrogen. You can just buy liquid nitrogen and use it to run your liquid xenon system. Okay. You can continuously purify the liquid because it's a noble liquid. You can just take everything except that out. And in LUX, that means we have to take our liquid, heat it up, clean it through a getter, like a catalytic converter on your car, condense it again. And one of the great innovations of the LUX experiment was making this a very efficient process. And that was a great thing that happened. Okay. You can make one big detector. It self-shields. And one thing, its density is so large. Its density is 3. Apparently there's a YouTube video of someone floating a piece of aluminum in liquid xenon, which I'd love to see that. I've never seen that. But okay. That's how dense it is. It's somewhat denser than aluminum. And in the end, you can make one big so-called time projection chamber. I'll say what that is. And it reconstructs all the positions and everything. Okay. Well, let me explain how we get signal at all. Here's our background. Here's what signal would be. Background is electron hits the xenon. Electrons, like electrons, find them easy to knock out. Very efficient at making ionization. In our buzz phrases, ionization we call the S2 signal. Why, you'll see. But that's sort of the more normal thing. The thing we're seeking is WIMP hits xenon. Xenon atom recoils. Xenon atom, what's it going to do? It's not that good at making ionization. Okay? What it likes to do is find another xenon atom and form a short-lived dimer state. And of course, nobles don't form molecules, right? So it's a short-lived state. It decays and gives you a nice ultraviolet photon that then is not reabsorbed in the xenon media because there's no other xenon molecules around to absorb it. It just flies for meters. So this is just great. Okay, this is what we call the S1 signal, the primary scintillation signal. Okay, and it isn't exclusive. That is, an electron will make some S1 and xenon will make some S2, but these are what they're good at. Okay, this guy will give a lot of S1 and a little S2. Dark matter gives a lot of S1 and a little S2. Ionization gives a lot of S2 and a little S1. because of the complexities of all this, the S1 signal for the same amount of energy deposited here is different. And sometimes you'll see our energy scale, keVEE, when it's an electron energy scale. And then this is our nuclear recoil energy scale. And I had to say that because I'll forget it so quickly, so you know. OK, so then the way it really works, this is not our plot. This is from our competitor, Xenon 100. This is how it works. So here is a horizontal scale with the energy of the recoil, and all the action is up to 30 keV, as we said. And what's plotted here is something like the ratio of the S2, which is ionization, and it's technical, but OK, to the primary ionization, the light, which is S1. And you can see this is what you see from electron recoils, and it's distinct from what you see from nuclear recoils. And the whole art of this thing is calibrating these curves really well. That's the whole business. Okay. So here's how we do it. LUX is a bucket about 50 centimeters across and 50 tall, a little different, of liquid xenon. Top and bottom, these circles represent phototubes, 61 on the top, 61 on the bottom, easily capable of seeing single photons. And then it's all put in an electric field. And by the way, we always call this coordinate z. It's up and down. That's sort of usual. Particle comes in, maybe a WIMP, or it could be a photon doing a Compton scatter. First scatter makes the primary scintillation a bunch of light, the S1 signal. And over here, there is sort of degenerate with distance is a time scale where the first signal you see is little and is an S1. Then you also liberate some ionization that you drift in the electric field up, and here's the two-phaseness of it. There's xenon vapor at the top. You literally suck the electrons out of the liquid into the vapor, and it works. First time I heard this, I said, forget it. It's never going to work. I'm never going to get involved in that. I was so wrong. It really works. You can. I thought somebody's eyelash is going to be floating around. It's going to absorb the electrons. Forget about it. But it worked great. Okay, our efficiency is about 2/3, and we think we can get up to 80%. The electrons are sucked out of the liquid. When they get in the vapor phase, they're accelerated by an increased electric field, and they create secondary scintillation. Each electron here makes typically something like 8 photoelectrons is a typical value. Do I have that right? Yeah, that's about right. Okay. So it's actually a big amplifier. You'll see. So it's a whopping great signal. Okay. And there you have it. So again, S1 is the primary scintillation light. That's the main measure of energy, it turns out. Okay? Although they're a little bit entangled, but okay. S2 measures the ionization, and that enables the signal to background discrimination. Okay, so I've shown you the gadget here, or the schematic of the gadget. Here is the gadget. Always in a clean room. Phototubes go in this copper container. Copper is our main thing to work with. And then the whole thing is surrounded in highly white, reflected like snow. Think of going skiing in the snow. It's really reflective. It's so white it would blind you, if it were sunny. Okay. And then from the bottom looking up, if you were a photon, you'd bounce through this white stuff and hit a phototube eventually. There's one of the phototubes. Here's a cross section of. Well, this is a cross section of more detail of it. It has to go inside a thermos, a big thermos, a Dewar, or cryostat, and there's all sorts of services, and it's complicated. You have to apply the electric field. That whole thing gets put in a big water tank. That's been one of our responsibilities, and sort of hung from a stand, and all the cables and stuff come out the top. Our total xenon is 370 kilograms. A lot of it is sort of outside and around. What's in the central region is about 250. And then the edges, their radioactive background tends to interact more near the edges. So the quiet spot in the middle is about 120 or 118. There's the actual water tank before a lot of stuff was built up around it. Some dimensions and really pure water. That's something Dean and all of us learned how to do, is make really pure water. Okay. And there's a bunch of the graduate students, mostly some postdocs, that are standing next to the actual gadget. This whole tank was our responsibility. There's phototubes there, and we can see when muons go through here and reject those events. Okay. Last fall, we started to put the ultra-pure water in. I like this picture just because it has something happening in the side. You can see the waterfall starting to happen. And this is a picture looking down after we had the water in, and I want to say I dropped my keys and had to fish them out, but you wouldn't believe me. Okay. But to stand there and look down into this ultra pure water, it was so beautiful. I can't. It's one of those weird experiences. I didn't expect it to be so much fun, but I didn't dive in like Ray Davis used to do. He had a big water tank too, and he would go swimming in it. We don't go swimming. So here's Dean White, who's here. The first water that we ever got, the first ultra pure water. There's Susanna working on her. This is how we keep radon out of LUX. There's radon in the mine, and she built the system that does that. Well, here's a signal, an actual signal from LUX. And what you see here is a function of time versus this is the pulses coming out of the phototubes. And you could count from 0 to 120 phototubes along this axis, and only 4 of them really fired. This is the S1, very small spiky pulses. And there's, if you look at if you sum them up and look at a smaller scale, you can see it's actually a double pulse. This is, I believe, a krypton event. I'll tell you what that is. 1.5 keV. 1.5 keV. It's very tiny by this scale. Okay. And then you can see, whoa! Later, when the ionization drifts in and scintillates, you just get a whopping great, huge old thing. Okay. Well, how we calibrate this thing is with krypton, and there's this radioactive krypton in it. I don't know if you know where radon comes from in your basement, but it comes because there's uranium and thorium that decays. And radon, when they decay to radon, the radon says, I have no chemical relationships with all you dirt and everything. I'm just going to diffuse on out. And so there's a rubidium isotope that decays into krypton. Same thing. The krypton says, wait, I'm not rubidium. I'm out of here. And it diffuses out. And then we inject it into our experiment. It's got about a 2-hour half-life. So we inject radioactivity into our experiment. It's supposed to be the lowest radioactivity experiment. We inject radioactivity into it because we know it's going to die away in a few hours. And then we use it to calibrate. And this is a map of radius versus height. And this stuff just mixes in perfectly and gives us a really uniform calibration over the whole thing. It gives us some nice peaks. I'm not showing you what the peaks are, but it gives us some beautiful calibration peaks. And we can just, slice this thing. We have 1 million events. We can slice it up and just beautifully calibrate the detector. We did not invent this trick, but we're the first to implement it in a large scale. And when you make these big detectors that shield themselves, that's the challenge. How do you calibrate them if you can't get anything into them? Well, it's like you give them drugs. Okay. What's that? Oh, it is. It's just an excited nucleus and has a gamma emission, Phil. That's all, as far as I know. But they're keV level, so they don't go very far. So they could be like electrons. Okay. All right. So this, in the end, is the plot that we're going toward. Okay. And you saw a little bit of this plot. This would be recoil energy, but we like to use slightly more raw units that we call corrected photoelectrons. We correct for all geometric effects. And that's literally 10 photoelectrons, 20 photoelectrons, 30 photoelectrons. So this is the arena of our search. This is the ratio of ionization to primary scintillation light. We take the logarithm of it. And that's actually important. There's a lot more variation than this logarithm would sort of fools you into not seeing. Okay. And then what you see here is electron recoils for us would live. Here's the median of their distribution, and then there's plus or minus. Well, it's 1.28 sigma. That I believe has 80% of everything lives in there. Okay, 10% live on either side. Yes, how do we know that curve? I'll get to that. The WIMP signals live along this red line and live between the red dotted lines, and you can see they're separate. And the kind of question you say is, well, how well do you know those curves? What's the rate of electrons leaking down and faking nuclear? Those are the sorts of questions you got to ask. Okay. One thing on this plot, though, is these light lines give you the energy scale in nuclear recoil units. So 3 keV is that line, 6 is that, and there's a little bit of mixing of S1 and S2 to arrive at the energy. That's a long story. These are in the other units of electron recoil energies, and they're all way smaller. And this is like if you went to the dentist, that would be the energy they would measure. Okay. So how the heck do we calibrate this thing? Probably, in my opinion, the most stunning thing, of course a little technical, of several stunning things, including the circulation system, was we put tritium. We introduced another radioactive element into our super quiet, super low background detector, and this time it's tritium. Tritium has like 18 years, has multi-tens of year half-life. And it's like, well, this is one of those great cases. It was proposed to the agencies, and it was reviewed, and people said, you're crazy, you can't do it. Okay, but we did it anyway. And so the question is, how did you get that tritium out? And so because we didn't inject tritium, we actually took methane and exchanged one of the hydrogens with a tritium. So it's tritiated methane. Our purification system, the catalytic converter, whatever you want to call it, grabs the methane and disposes of it. So it's gone within a day. And what's great about tritium, it's a beta decay nucleus and emits keV level electrons and allows us to calibrate this electron recoil curve. Look how wonderful this calibration is. It's just the most beautiful, clean calibration. And that's how we determine this band, where the background lives. This red line is the midpoint of the nuclear recoil band. And you can start asking, the traditional way to do a WIMP search analysis is ask, well, how many events are below this band? And so we're able to calibrate our tails. And it's at the level of a couple parts in 1,000. Misidentification. Totally calibrated. Okay? Well, the only thing we haven't overcome is we haven't found something like tritium that emits neutrons yet. We have some ideas, but I don't think so. I don't think it's going to work, our ideas. We wish we had some chemical that emitted neutrons that we could put in, and it would spread out all over the detector and allow us to calibrate. So we still have to use external sources. Americium beryllium is a famous one, and californium is a fission source. This is one where americium illuminates beryllium and knocks out neutrons. So this is our best we can do on a calibration of what the nuclear recoil band would look like. It's dirtier than WIMPs would be because these guys come with all sorts of extra gamma rays and junk. And we model that, and our Monte Carlos look just like that. So we use these curves to really calibrate the heck out of our device. And there's all kinds of things I could say now I might skip over because they're technical, like the leakage of electron recoil below the nuclear recoil band. There it is. Below a couple 10 to the minus 3. Red points, I believe, are Gaussian modeling, Gaussian fits. Black points are the actual data. The tails are good to parts in 1,000. Okay. Yeah. Sure.
Increase the amount of tritium you have, and therefore increase the tails.
Yeah.
You model to see indeed whether your Gaussian approximation, whatever approximations are valid.
Yeah, at the level, we've sort of probed 10 or 20 times the level of that we need for the data in CNO tails. But we'd like to do, 1 million times as much data as we have. We haven't done that yet because we wanted to get out and publish a result. But yeah, we'll do that. And so there's the leakage. There's detailed issues of this. It tells you how many. This scale is what you want to see as a function of nuclear recoil energy. What are we assuming for how many photons per kilovolt? And this purple curve is our thing. And we make there's no data in the world that goes below 3 keV. So we don't take credit for anything below 3 keV. We just imagine the response is 0, and that gives us worse sensitivity. Okay, but that's what you got to do. Our curve is the purple one. Our competitors, Xenon 100, use these black points. So they're assuming they get better light than us. That's actually important when comparing our limits. Okay. There's all sorts of studies of the efficiency of how we turn on as a function of signal. There are details, we could come back to them. And more modeling that drives our Monte Carlos. And in the end, these black points, as a function of the true recoil energy, I can tell you if there's a Xenon that recoils with 5 keV, our assumption based on fitting all sorts of data is that 65% of the time we're able to see it. That's what this curve gives you. Okay, so that's the detector response. Now the actual data. The first thing with the data is what we call our high energy sample. Okay, so this is what you do. If you just take any piece of matter in this room and take it to a low background facility and say, is it radioactive? You end up, the low background facility will give you a plot like this. And you'll say, well, what's that all about? Okay. There will be thorium or uranium, and they give a bunch of gamma peaks. So surrounding our experiment, the phototubes, just any smudge will have a little bit of uranium and thorium in it, unfortunately. Okay, we keep it to the minimum, but there's always some. Okay. And so that's a thorium-related peak. These are uranium peaks. Look at the energy scale. It's MeVs of energy, thousands of keVs of energy. But the point is, this is like the source of gamma rays that surround our detector, and are shining gamma rays into the center. And what can happen is those gamma rays can Compton scatter and give us a background. So quantifying this is really important. And it's pretty good. There's a little disagreement there. We think we understand it. We think we don't really have thorium, but we actually have radium. Radium, we don't talk much about radium in polite society anymore. But anyway, we think we have a little radium. Okay. And then what happens is it allows you to extrapolate down, and you can see this is attenuation. Lower and lower energy things get attenuated, but we can predict now from this how many events live in this band. Okay? And we have a way of quantifying that. And it's this table. So gamma rays from the outside. So there's a way to quantify it. It's how many events per kilovolt of electron energy per kilogram per day. That's the traditional unit. My old experiment, CDMAS, that 10 to the 3 wasn't there. It was ones of these units. This experiment, we gained a factor of 1,000 on our background. Okay, so 1,000, and the dominant one is from all the uranium and thorium and stuff, and potassium and stuff, about 2. And we've measured the heck out of that. That's somebody's thesis. Okay. There's literally some xenon that has a 36-day half-life that was activated when the xenon was at the surface. It got a little bit of its own self-radioactive, and it's dying away with a 30-day half-life, 36-day half-life. That's the second biggest source. We always have a little radon. That's, it's actually not our radon. It's somebody else's radon. There's an impurity somewhere that's leaking radon. And krypton can come with xenon. There was this enormous effort to take natural xenon and remove its krypton, removed by a factor of 10, almost 10 to the 5th, which is a huge effort. And the way they did it literally was shine the gas through a tube, and it's not really a tube. It's really a tube filled with charcoal, and the krypton goes faster than the xenon. So it's as it might. Okay. So that was a huge effort. And so this quantifies our background, and that's actually prediction, and that's actually a measurement. They're in pretty good agreement. We're working on that. Here's our data in the end. Okay, 86 days we took data during the summer, and just to say, we started with some 85 million events read out. Actually more than that, but that's a detail. And events that look like they just have a single scatter. Most Comptons do multiple scattering. Most Compton events do several scatters. Single scatters are only 6 million. Then our low energy region is a very small fraction of everything, down to 20,000 or so. And then the next two cuts are the fiducial volume, the very core middle of the detector. We're down to 160. Okay. And those 160 are distributed in the detector like this. So this is radius. We usually plot radius squared because volume is proportional to radius squared. And here's the height. And our center region is the quiet region. You can see there's all sorts of events near the edges from the radioactivity. But the center region is where we look. And it was pretty fair the way we determined this. That's a long story, how we determined this box was the box. I should, at this point, say we didn't blind our data. I don't want to pretend we blinded our data. Don't get, why did we not blind our data? This was an engineering run where we thought, we don't know what's going to happen. This is the first run of the detector. We just have to understand the detector on this run. Okay, so there's the 100. They look pretty uniform. A WIMP signal would be totally uniform, right? Okay, maybe not quite uniform, but pretty close. Gee, am I there yet? Yes, I am. I'm actually sort of on time. All right, here they are on the key plot. This is it, just right to the point. The 160 events on the main WIMP search plot. Here we are versus that thing that's like nuclear recoil energy or the primary scintillation in photoelectrons. Our threshold is actually 2 photoelectrons, which is near 3 kilovolts. And here is the ratio of ionization to primary light. The blue, they'd cluster around the blue if this was background. They'd cluster around the red if they were WIMPs. Look at it. They cluster around the blue, right? Okay, that's the dominant thing. And then you can get into, we also formally, this is our search region. The 160 events live in here. You can start asking about, okay, well, what about these events that are just outside the blue line? And it turns out it's approximately 10% of the 160 are outside the blue line, and that's exactly how the blue line was defined by our FITs, was to be the point where 10% are outside. There's one event that's a possible candidate, okay? And the thing is, it's the expected background to fall below the red line is 0.6 events. We can't say there's any signal at all in this. Okay, so what do we do now? These days, we all have to do what the Higgs search did at LHC. We have to do our statistics the same way. Okay, not actually because it's good. It's not just because they push us around. All right, so we do a big fit to this whole thing, and we have a model of the background and the signal. Let me see. Yeah, it looks like these are the conclusions. We don't do a search box. We do a 4D fit. To this whole plot, those are two of the dimensions in this radius and the z. And here are projections of that fit. So this is projection in S1, which is like the energy, and there's the data and the fit. Looks pretty good. S2, and then here's radius. Should be radius squared, but okay. Most of the events tend to live near the edge. This one we stare at and we argue about. It looks like there's slightly more events in the center. We think there's a little more radon than our model has, if you really want to know the truth. But it's a pretty good fit. And then Z, the events cluster near the edges. And it's consistent with background. Yeah. Oh, here, I'm sure it's just root n. I mean, this one must be Poisson. That's an interesting point. Well, I actually think that the square root of 4 is 2, so all of these have error bars that are 2. Is that what? You think so? Louis Alvarez would probably argue with you. He used to count the number that were outside the. Yeah. Okay. All right. So this is the way you set a plot these days, or way you set a limit these days. And the Higgs people, the CDMAS, LHC people will recognize this plot. This is what you do is you keep adding, forcing signal events in the fit, and then make a parameter that tells you how bad the fit is. That's basically what's going on here. And when it crosses a fit that is sort of only 10%, what happened 10% of the time, that's the limit. And somehow I've lost the, that's it. So this is the 7 GeV limit, about 2.4 events. So there we go. You can do that for many different masses. And what you can see is as a function of the mass of the WIMP, 10, 100, this is our high mass limit, you would say. This is our current limit. The blue is minus, we could have gotten 1 sigma worst limit, or 1 standard deviation worst limit would have been up there. If we'd been lucky, we could have gotten a limit as good as that. We're kind of in the middle of the range. We got about an average limit, okay. And, okay. So, and then you can start to see some comparisons. Here's the previous world sensitivity holder, Xenon 100, who ran about not quite 3, about 2.5 times as long, okay? And that's the ratio of masses. And then their earlier thing. My old experiment, which we had a big to-do in 2009 with our last results here at the KITP, if you remember. Okay, look. Almost 2 orders of magnitude in 4 years. It's amazing the sensitivity that's going on in this business. Okay, then you can say, well, what about up here? That's where all the sort of what I call the left wing is. Okay, so here's just a transitional plot that shows you, everything. We spent an enormous amount of time understanding our detector response down here. We have a lot of confidence in this curve. We think the main uncertainties are astrophysical. In there, we just have to rest on the fact that everybody uses the same astrophysical model of the galaxy. So at least we're kind of comparing apples to apples. You can start to argue that some of that different galactic models would shift these a little bit relative to each other, and people write papers about that. But everyone tries to use the same astrophysical model, so it feels to 0th order like apples to apples. So if we blow up that region, here you can see our sensitivity. Everything below is allowed, everything above is ruled out at 90% confidence. And you can see this point that got a lot of attention from the CDMAS experiment where there are 3 events. If that were reality, and if all the assumptions are right, that you have spin-independent scattering, coherence, all galactic model, all that stuff, we would have seen about 1,500 events. Okay, I can show you what that looks like in a second. That's it. I should stop for a second. I have a few more slides on the future. Very good. All right. So what's the future? we weren't convinced we knew how to blind our data because it's complicated, and we weren't convinced. And part of that is just knowing what the backgrounds were, and you don't want to blind the wrong thing or blind the thing you really need to sort out background from signal. You want to keep out of the signal region, but you want the background to be sort of, have a handle. We're going to do a 300-day. That's about 3.5 times as long as the one we've done, and that's just sort of a year. That's the working part of a year on these experiments. And we think we'll get about 4 times the sensitivity in that year. We have a proposal to upgrade to the so-called LUX Zeppelin. Zeppelin was a UK experiment with liquid xenon, an excellent experiment. And so LZ is LUX Zeppelin, 20 times the mass. And basically, this is the biggest we could fit down the shaft in the mine and fit into our water tank. And we thought, look, I mean, if we don't ask for the biggest, then later we'll ask to upgrade to the biggest, so why don't we just ask now? Okay. 20 in mass, lower backgrounds, factor of 100 in sensitivity, down to 10 to the minus 48 centimeters squared. We start to get into the background from atmospheric and solar neutrinos at that point. You're not quite hitting it real hard, but it's starting to, you're getting maybe a few tenths of an event. Okay. If somehow spigots of money opened up, it could be online in 2017, but what are the odds of that, right? That's what it looks like. It's the same water tank and the same guy standing there. But there's a few differences. It's a much bigger liquid xenon area. And then we believe, we know we need a much better veto. What can happen is these gamma rays that come out of the phototubes can scatter once and then leave the detector. You want to be able to identify them. Okay. And that's what this scintillator veto is doing. Then there's all sorts of other tubes. It's really quite advanced stage. This is the future of the whole field. This is a plot I normally would never show. It's just one of those plots that's too complicated. Okay, so it's the WIMP nucleon cross-section over, 11 orders of magnitude in the WIMP masses, and all the different experiments you can think of. This was done the summer before our result. The LUX result has turned out to be a little lower, particularly over here, than was projected during, this was for the so-called SNOWMAS process, okay, was made. You can see LZ, in principle, would be the most sensitive by 2017. And then this gives you a feeling of where atmospheric neutrinos start to lay. And this is where, to be honest, if we want to go down there, we have to build better bridges to people who care about these neutrinos. Okay, that's what we'd have to do. And then the left wing has a bunch of proposals to get more sensitive, and there you build detectors that are sensitive to smaller and smaller energies. And they run into coherent neutrino scattering from the sun rather than atmospheric neutrinos. And thank you.
Questions? Should use the mic. Let's use the mic.
Yeah.
What about the spin-dependent scattering?
Yeah, very good. Xenon is great because it has all sorts of different isotopes. It has 5 or so stable isotopes. And the key to doing spin-dependent is to have an unpaired nucleon. So even nuclei are kind of bad. But if you have a nucleus that's odd in some way, it has a spin sticking out. And xenon has a few of those. Now, they tend to be the neutron-rich. Okay, so you get into this argument of we're neutron-rich. Iodine, sodium is proton-rich. So there you have legitimate possibility of isospin dependence because traditionally the weak interaction has that, by the way, okay, in it. Well, it's mainly the vector part. So we do the neutrons, we do that real well. The protons tend to be done real well by astrophysics because the sun is a big bag of protons. Annihilation's in the sun, dark matter collects in the sun and annihilates. So that's where the really great sensitivity is there. So that's the sort of way we look at it. We'll probably have a paper out in a few months on that one. So.
Harry, if you go back to the curve showing the different experiments, Can you give us a sense of the ones that are active right now? It's hard to know from this plot.
Yeah, this is one of those plots.
Who's real and who's imaginary?
Yeah, Xenon 100 existed. Darkside 50, I think, is funded and operating, and they don't have a result yet. So they're in Gran Sasso in Italy, okay? And they're argon. Darkside 50 is argon. And then, let's see. Super CDMAS is going to work at Snow Lab. They've been working very hard to make super sensitive detectors at low energies. So they're very active, okay? And then I know COOP must be on here somewhere. They are extremely COOP. COOP has an upgrade, and they're really starting to operate in the Sudbury mine. Okay, so they're the successor, and I'm embarrassed to not know the name. Pico is a thing that's like COOP but different, and they're very active. Deep is a big, what we call a single phase experiment. It's a big ball of liquid argon, sort of like the snow experiment was, except the snow experiment had heavy water in it. This has liquid argon in it. They're very active, and the Canadian government has been quite supportive of them. Okay, and then Xenon 1 ton got their Xenon, and one of the things you could ask me about is who controls the world's Xenon, and I would ask, it's Dr. No, obviously. But anyway, somebody in his volcanic basement hideout in the Caribbean has all the world's Xenon because the price has been going up and we don't know why. Okay, and the great thing about Xenon 1 ton is they got all their Xenon already. So they, well, some people would say it's because they have good relationships with Spectre, but never mind. Okay. Whereas James Bond is too old to get us our Xenon. So anyway, okay. So the Xenon, getting Xenon is an issue. They've got theirs, and the thing that's really going on is they're putting together the similar technology for cooling and recirculation that LUX did, and it takes a little while to master that, but they'll get it eventually. Does that help?
Yeah, that's fair.
Yeah.
David?
So I didn't see any neutron background, which was a frequent background in previous experiments that would, say, come from cosmics that you failed to veto. Yeah. Why not?
We think it's below, sort of a 30th of an event. We think it's so low, and we think it's low, so we're way deeper than we were at Sudan. We're roughly twice as deep, and so I forget the power law, but it's a pretty high power law. So at this level of exposure, it's not yet. The cosmogenics are not yet a concern. In the longer exposure of LUX, we think it will be important. And we do have photomultiplier tubes in the water. And for various reasons, they weren't really in the data acquisition during the run. It was one of those things that they should have been. And so for the next run, the Santa Barbara group, of course, is leading the effort to turn on the water-based veto system and be able to reject the cosmogenic production. But for this run, we wanted a result. We sort of made a beeline for a result and decided to
and the depth that just means that you really don't have to fight hard to veto until you get a big exposure.
Right, now, there is an empirical thing in our paper you'll notice. Neutrons multiple scatter. The ratio of multiple scatter to single scatter neutrons is, 17 to 1, something like that. So if we had a neutron background, we'd see it in multiple scatters long before we saw it in WIMP scatters. And so based on that, we have an upper limit that's about a third of an event, I think. And that's a very, and that's Poisson. It's because we have 0 multiple scatters, and you get to a third of an event in single scatters or something like that. Or I've got it a little bit off, but it's close to that. Okay.
Okay, thanks.
Yeah.
All right. Phil, hang on a second.
Eric, can you explain why the atmospheric and coherent scattering background rises so rapidly at 10
This thing right here?
Yeah.
Because it's a different physical process. So this isn't atmospheric anymore. These are solar neutrinos. So basically, if you were to build a nuclear recoil WIMP experiment that could get sensitivity to 10 to the minus 46, you would do solar neutrinos with it by their elastic scatterings. Does that?
Effective energy at the WIMP mass recoil. That's what's.
Yeah.
The x-axis is weird in that instance for you.
Yeah. It's just up here, the neutrinos from the sun just don't have enough energy to bump a 100 JeV nucleus and give it enough energy for us to detect. That's all. It's kinematics. Okay. So when we're at high masses, nobody has sensitivity to the low recoils that a solar neutrino would give. That's it.
It's really not mass. It's just energy.
It's because. Oh, I see what you're saying. Okay. You could say it's cross-section above some recoil energy. That you have to integrate above some detectable. So it's a cross-section above some. Yeah. So that's. It took me a while to understand why it was so confusing, but now I understand. I think we do an integral from a minimum energy also. Okay.
All right. Thank you, Harry.
Okay.